All right, so sorry about that. Okay, so then so we were talking about this a little bit here, right? And then null hypothesis, alternative hypothesis. So effectively, like the idea behind these things is that there's some parameter of a distribution you're interested in finding out what the value of that parameter of the distribution is, right? Not the statistic from the sample, but the parameter, right? So then the parameter of the overall population, you want to know what that is. Given you want to know something about the parameter of the population, like people generally will assume or claim some sort of value, right? So, like, if you go to a particular situation, people start saying, oh, the average height of the people in this area, we think is 6 feet tall or something like that. Or the amount of money that they make in this area is on average $25,000 or whatever. There's some number that they think it is, right? But then the thing is like the idea of a hypothesis test is that if you were to observe some sample that was randomly collected from this particular distribution, and if that value deviated from the value that was claimed, right? So for instance, if we sat here and we said, oh, people start randomly coming to the school and we start selecting those people and then randomly, obviously, and then we're going to determine like an average based off of these people that we're randomly selecting. And we determine that the average height of the people that we're randomly selecting, let's say, is 7 feet tall. Okay. And let's say we've randomly selected, I don't know, 50 people or something. If someone's making this claim that the average height is, let's say, 5'6", then given your sample, if your sample is randomly selected, maybe you would start considering that maybe the 5'6" might be erroneous. Okay, because there's kind of no way that if the average was 5'6", that if I randomly selected 50 people and those 50 people ended up having average of 7 feet tall, the chances that that actually would happen would be kind of small, right? And since it's so rare that something like that would occur, given the fact we're assuming that the actual height is 5'6", then maybe there would be an issue here, right? Maybe the values would be so significantly different from each other that we would start claiming that our original claimed result or assumed result was not correct. Does that make sense? All right. But if we said the same thing, that it was 5'6", and then I grabbed 50 people randomly, and then their average height was 5'8", maybe you would start telling me you're not sure if this is significantly enough different for you to claim that the original height 5'6" is not appropriate. Does that make sense? So the question is like, where do we define this like cutoff line where on one side we'll claim that it really can't be changed, or we think that the original assumed value is correct, and then the other cases we start saying that really the assumed value probably is not correct, given the fact that the value is so significantly different from what we think should be occurring. Does that make sense? Question? Well, so that's the thing. That's a very good question, actually, because the thing is I should have said that the one thing about statistics that's kind of aggravating is you can never actually prove anything. Okay, so like, there's never a case where we're going to be able to say, hey, you're wrong. Okay, and that's actually the example I'm going to go into in a second right now. But I can say beyond a reasonable doubt you're guilty. I can say given the evidence presented, there's a statistically significant. It's statistically significant the result that was observed. Therefore, I think that your original claim is probably not correct. But I can never actually say your claim is not correct. Okay, so one sample of data has been gathered through an observational study or experiment. Statistical inference allows analysts to assess evidence in favor of some claim about the population from which the sample has been drawn. The methods of inference are used to support or reject the claims are called tests of significance. Every test of significance starts with a null hypothesis. What do you know the word null means? Zero. That's true, but the only problem is that null, I like to think more in this case, like the meaning is more like from computer science. When do you use like null in computer science? What did Catherine say? The emotion is true. But the if you consider an array, right? And then we don't put the value into the array, right? then the value is still considered to be a null value. So for instance, like if you're going and you're typing in your password or whatever, you're logging in some website, and then you don't write a username, right? And then you push enter, that's technically a null value. It doesn't let you go through. Does that make sense? All right, so null is sort of like the base level assumption or the lowest possible thing. So they start writing it with like 0. Does everybody see that? So then the idea is like if you were to do a hypothesis test, you're going to check like if based off the null hypothesis, we're going to compare other hypotheses possibly. So then we would start calling those, let's say like H1, H2, etc. Does that make sense? Now, each of these hypotheses should be sort of like disjoint from each other so that we can make a clear decision whether we think it's H0 or H1, etc. Does that make sense? All right. So then instead of writing H1, H2, H3, because in this class we really don't have multiple alternative hypotheses, we'll only have one usually. So I'm just going to call it HA, the alternative hypothesis. All right. So every test of significance begins with a null hypothesis. H0 represents a theory that has been put forward either because it's believed or true, because it's used on the basis of an argument, but has not been proven. For example, in a clinical trial of a new drug, the null hypothesis might be that the new drug is no better or on average than the current drug. I think this idea is extremely important because this gives you an idea of why hypothesis tests can be so useful. So for instance, if you wanted to check like if people were being racist or something, right? And you have these two groups, and then there's one group over here and there's one group over there. And then we randomly select people from the first group and randomly select people from the second group. And then we start determining that some property about these people is like different between the two groups, right? Then the thing is what we'll do initially is assume the two groups are the same. But then based off the treatment that occurred and the properties that results, there exists this difference. Again, if this difference is significantly different, right? Then we would start saying, hey, maybe there's some sort of different behavior that's going on here. Maybe these people are actually being treated differently. But again, maybe, we're supporting this assumption. It's not really ever proving anything. Okay. But if you think of, Brown versus Board of Education and Plessy Ferguson or whatever, and those things, and then you start talking about separate but equal in Alabama with those schools at that time before civil rights, right? Then that was effectively what they were saying. Like it was a court case where you started saying that now all of a sudden, as soon as you make it separate, the two separate systems, they're automatically actually not going to be equivalent anymore, right? And then if you start dragging people and telling them that they have to drive a very far distance to get to the school and there's no buses and there's no this, and then some teachers won't want to go there, obviously these students are going to be treated differently. So then this is an example of some case where you might do some sort of hypothesis testing to prove that maybe you need the integration of the school. So anyway, the alternative hypothesis is a statement of a hypothesis test is set up to establish. So the alternative hypothesis is what you actually want to show is true. So something in the question is going to state what you want to show. Does that make sense? The alternative is the thing that you're always trying to show is true in this format. The null hypothesis is the assumed sort of thing that everybody thinks is correct. Does that make sense? All right. So then so everybody thinks something. I think otherwise because I've observed these samples and I've seen these differences. And then based off of the observation that I'm seeing, I'm going to use that to try and see whether or not this could just occur by random chance, right? As he was saying earlier. If this can just occur by random chance, we're not going to give up on our null hypothesis. We're going to say that's still accurate. Like, for instance, what we were discussing when the average of the group was 5'8" versus 5'7", right? If you're only selecting 50 people, 5'6", sorry, 5'6" and 5'7", 5'8", whatever. 5'6", 5'8", thank you. So then if it's 5'6" and then the other person, then the average was 5'8", right? Then if I'm randomly selecting 50 people, we would actually have to calculate to see if this was actually going to be significant or not. But if I started increasing the number of people that we were selecting, right? So if we started selecting, let's say 1 million people, all right, and then we randomly selected those people and the average of those people ended up being 5'8", and then our assumed average, or from our null hypothesis, was 5'6", what would you conclude then? What'd you say? So once you're selecting 1 million people now, all of a sudden, it becomes much more difficult for the average to change greatly, right? That's effectively the central limit theorem. Is that right? because the central limit theorem, the standard deviation becomes sigma over square root of n, right? So then the standard deviation becomes very small. If it starts becoming very small, then getting these differences to exist becomes extremely not probable, right? So then you shouldn't be just seeing events that really shouldn't be occurring all the time. Is that correct? You didn't just get super lucky and win the lottery today, right? Maybe the thing we're assuming is the problem. Maybe the thing we're assuming is not correct, or the null hypothesis. Does that make sense? All right, so then eventually we're going to have to make a conclusion. The final conclusion, once the test has been carried out, actually this part I'm not going to read it because I don't really like the way they state this here. All right. All right. So let's talk about some sort of court case first. All right. So like if we have a court case, what would the null hypothesis be in the court case? Wait, innocent? Is that what you said? Innocent? Because in the United States, we say we're innocent until proven guilty, right? Well, in reality, they don't actually kind of say that. No one ever will turn around and say anywhere that someone is innocent. There is no such thing. You cannot prove someone is innocent. It is impossible. You know, they don't even prove not guilty. And this is the thing that's weird. But if you think about this in terms of this hypothesis, that it gives you an idea of what types of conclusions are actually possible. Does that make sense? So then the thing is like, you can't really ever show someone is innocent. Why? So let's say like Jeff is a murderer, all right? Let's say there was like some bloody glove. There was this knife. He was holding the knife. There's blood on his shirt, right? He says he's not the murderer, but like there's all this evidence that seems to suggest he's the murderer, right? So when you're going to have a court case, why would we have the court case? When do you have these court cases? When there's like a probable cause, right? Or some sort of evidence that we would suggest that we think this person has perpetrated the crime or whatever, right? So then the thing is if this individual has, you know, if we have this evidence, then we go and we start having this trial, right? In other countries, some places, they assume you're guilty first. And then it's on the defendant to defend the defendant, right? And then they have to sit there and start saying now they have to prove that this person is actually not guilty. Is that correct? Right? But in the United States, it's not the way it works. We assume they're not guilty, and then it's on the behest of the prosecutor to turn around and prove that they actually are guilty, right? I think you know what country you live in. No. No. There are Broward College campuses all over the world. Because those students take it to a separate campus. Imagine that. That's a terrible question. All right, so then the thing is that and we will move on. So then the thing is though that like when you're doing this, right? So what is the assumed hypothesis when you go into a court case? What's the null hypothesis? What's the null hypothesis? Come on. Well, we can't say innocent because actually there's no such thing. Why can you say not? Why can you not say innocent? Because the problem is like I was not there when the murder actually occurred. I cannot sit there and start saying what definitely happened. All we're going to be able to use is like a bunch of different evidence to say, hey, we think this isn't what could have occurred. Does that make sense? Right? Beyond a reasonable doubt, we were not able to show you were guilty. Is that correct? Right? Then you're not having a trial. That's a terrible question again. So then sorry? There's no terrible questions, there's only terrible people. Correct. So then the thing is now so in reality, the assumptions actually become like this, that the null hypothesis is not guilty. The alternative actually would be that you're trying, right? When you're having the trial, we're trying to show Jeff is guilty, right? He's the murderer, right? So we would want to show he's guilty. That's why they have the trial. No, that's not why you have trials. That's the only reason why you have the trial. Right. That's all right. So then I'm not sure bloodthirsty was appropriate. All right. So then the thing is that they have these, so they like to, you have to be able to phrase these statements in such a way so that anyone anywhere will understand what the conclusion means without actually completing the hypothesis test. So there has to be like some conclusion at the end that you write, like a one sentence type thing that has to have some sort of practical significance that anyone can understand. All right. So then so what we say here is like these are kind of the two conclusions that we can end up making. We're trying to show the person is guilty. Does that make sense? So we can either say there is significant evidence to suggest that the person is guilty, or beyond a reasonable doubt, given the evidence presented, right, in the court case, we find the defendant guilty. Is that correct? Right? So then that would be this case here. Then the other thing is that they don't actually ever turn around and be like, oh, you know what? Jeff didn't do it, right? Jeff's not a murderer. They just turn around and say, hey, you know what? We were unable to show he was guilty. Does that make sense? Right? So then that's what non-guilty really means. Does that make sense what I'm saying? We were unable to show you were guilty. Is that correct? So then the thing is like, all you really say is there's not significant evidence to show that the defendant is guilty. You do not ever state that there was enough evidence to show they were not guilty. You do not say anything like that. You just start saying, I was not able to show the alternative. Does that make sense? So then these are the two formats of the conclusions. There is not significant evidence to show HA. There is significant evidence to show HA. Effectively, once you know what HA is, you just regurgitate it back in these sentences. Does that make sense? Right. Correct. You never, so like even saying like I accept the null hypothesis is kind of erroneous also. Okay, like this Yale thing here actually says that. It says that you can reject HO in favor of HA. Okay, you can do not reject HO. All right. So sometimes they call this the ho and the ha. So the idea is that you want to reject the ho. That's the point of the test. Does that make sense? And then, but this is like common terminology. Either they say reject the ho or they say fail to reject the ho. Does that make sense? Now in England they'll call it H naught. All right, but and then sometimes people call it H0. Sometimes people call it ho though. All right. So the thing is that that doesn't make any sense. There's only one in this case. So then come on, stop being silly. Stop being silly. All right, does this make sense? All right, you need to understand. You need to understand what this terminology means here, okay? Because there will be questions that are phrased in terms of this terminology. All right, so then now, generally in this course, we're not going to do the standard deviation stuff. So all you're going to have to do is really ever determine if something is a mean or a proportion. Does that make sense? And for the most part, unless the question gets more involved or whatever, but rarely is that going to happen. So the thing is that you must assume something in the null hypothesis, right? And it has to be about a parameter. Does that make sense? So this is generally the way it'll be written. Mu is equal to mu naught, where mu naught is some fixed value. So assumed, this is some assumed or claimed value for the mean in the null hypothesis. Then these are the three choices that we end up being able to do in terms of the types of hypotheses that we're going to usually deal with. So either I try to show that the mean is actually larger than this value, I try to show the mean is smaller than this value, or I try to show the mean is not equal to this value. We'll give examples of this in 1 second. This thing here, these two are called one-sided tests. This is referred to as a two-sided test. Does that make sense? All right. Sometimes they could also call them left-tailed and right-tailed also. You'll see what that means, though. It's very obvious. Question with this? So proportion, same thing, right? So I always give an example about like the election associated with Donald Trump and Hillary Clinton. And like, you know, there's an assumed proportion that someone's going to get, right? But the thing is if you think about it, like elections really are a hypothesis test. Does that make sense? What's the null that the proportions are equal? Sorry? That you assume that the proportions are equal to each other. Because I'm having the election to try to show that we're favoring you versus, let's say, Jack or something like that, right? I mean, that's a different argument. But the thing is like but if I was favoring one candidate versus another candidate, right? Then the way you would want to prove that. Okay, so the problem is that you're always really sampling when you're doing an election. Is that correct? Now it's not necessarily random, so that causes some major issues, honestly. But let's just forget that part because we can't even resolve that. Okay. So the thing is like you have this selection of people, which unfortunately is not so random, right? Now, like I don't show up to the election. You don't get my information, right? Now the thing is if there's a lot of people like that don't show up, now all of a sudden we might actually get the wrong result. Is that correct? Right? But the people show up. Okay, so we know though there's some sort of variation associated with the results in who shows up on what particular day, right? You might have got a car accident. There might have been an issue. Someone might have passed away, whatever, right? So then the thing is like these things, like there are these issues that can result. So you get different groups of people that end up actually occurring, right? And then you would get different p hats or estimated proportions in the situation, right? Now the problem is like there's going to be some variation associated with these p hats. The best way to do an election would be to sit there and say, hey, I'm going to keep sampling and sampling and counting and counting and counting, right? And then I'm going to stop counting at a certain point because I've already realized the proportions are actually significantly different from each other. But if they're too close together, I have to keep counting and counting and counting and counting and counting. And then eventually I'm going to get to close to the end. And once I start getting close to the end, I'm going to still be able to say that I can construct confidence intervals about these things, and those confidence intervals wouldn't necessarily overlap anymore. Does that make sense? But confidence intervals and hypothesis tests are directly related. So every time you do a hypothesis test, you could do it through a confidence interval, or you could do it with this process we're going to do in a second here. But the point is that if the differences were not so significantly different, right? Like if we were off by 1 vote, they voted you 1 vote more than me, right? If they did that, I'm going to have to count everybody. Otherwise, I'm never going to be able to actually tell what's going on in the situation, because sometimes it's going to seem like you have 5 votes, I have 5 votes. Sometimes it's going to seem like I have 4 votes, you have 6 votes, or etc. And then sometimes it's going to seem like I actually have 6 votes and you have 4 votes, depending on which ones are counted. Does that make sense? So then the problem is you're never outside the margin of error. So then you can't conclude that there's a rightful winner. So you would actually have to count everybody. Does that make sense? All right. So then the all right, any question with this? All right, so then let's just briefly explain what I mean by one-sided and two-sided here or something. So like if the mean is equal to 5'6", and then I was trying to claim that the 50 people showed up and they had we randomly found these 50 people and they ended up coming from the same distribution and they had a mean of 7 feet tall, we would start claiming that maybe this is actually too significantly different from this, therefore that maybe the mean is actually larger than 5'6". Does that make sense? So we would try to do a hypothesis test like this. Does that make sense? Now, what I'm trying to draw here is that I'm trying to indicate that at some place over here, right? I don't know where necessarily, and that really has to be predefined before we start this process, all right? But somewhere here, maybe there, maybe over here, wherever, every value past that point or to the right of that point, we're going to claim is significantly different from 5'6". Does that make sense? All right. But the thing is like, this is the value that I ended up observing this time, right? From my sample, all right? So given the fact that we assume, right, this is the assumption, right? So we get to assume the mean is actually equal to this, right? All right, well, if we sample 50 people, X bar should follow a normal distribution with some mean and some standard deviation. Is that correct? Where the standard deviation would be sigma over square root of n if sigma is the original standard deviation of X values, right? But well, I didn't state that here. But the thing is that I'm just trying to explain what one-sided and two-sided means. So then the thing is this, but I would be able to apply this because 50 is larger than 30, and then the central limit theorem does apply if these people were independently selected. Does that make sense? Now the thing is I can't really do this though. And you just brought up a good question. What is sigma, you said, right? But like, would you really know what sigma is? But no, but we infer. All right. So then, like, correct. So what is sigma? Sigma is population standard deviation, obviously. Oh, okay. So that was a push for me. Okay, so at least I passed. All right. So then so then sigma population standard deviation, we would need that to calculate z-score, obviously, right? Z-score is going to equal to what? X bar minus mu all over sigma over square root of n, because we write the mean of the distribution here and we write the standard deviation of the distribution there, right? And this is the observed value of interest or sample value there. The problem is we're never going to know what sigma is, right? So you would use the best estimate, which would be what? Since we have nothing else, we would have to use the sample standard deviation. But then once we start using the sample standard deviation, that we can't use z anymore, right? So then we have to use the t distribution. as we stated previously. All right, so then the degrees of freedom for this distribution, as we stated before, was n-1, just because you're using the average to calculate. Anyway, we'll talk about it again. All right, so then but the thing is like, so we have to use this t distribution, but again, t distribution has more or less the same shape as a normal distribution. But we have to say, like, is this difference significant here? Is that correct? Right? So then there ends up, what we do is for the one-sided test, we end up defining a region over here where we call it the rejection region or alpha region or something like that. All right. So we have to define what alpha is before we start, right? You're never going to get in. So then so alpha, right? The alpha is they say the probability of a type 1 error, which is the probability. How would you state that? What is a type 1 error? Do you remember? But wait, let's just try and think like what types of errors we could make here, and then somehow this becomes obvious because this is the first type of error that you would really ever think about. Okay. So then the thing is you're assuming the mean is equal to this, right? There's only two types of errors you could make, really, right? You can either, the mean is actually correct and you think it's not. Does that make sense? Or the mean is not correct and you think it actually is. Is that right? Right? So the thing is what would the normal type of error be? Well, alpha, I'm going to claim, is actually that this area of this region over here, we're going to define that to be alpha. Does that make sense? So then alpha would mean the probability of thinking that the mean is actually different than this value, given the fact we assume that the mean is actually this value. Does that make sense? So this is the mean is not equal to mu naught, given that the mean, we assume the mean is actually mu naught. In other words, or excuse me, we were saying greater before. In other words, it's the probability that the alternative hypothesis is true, given the fact that null hypothesis is true. Does that make sense? Does that make sense? All right, now, this region here, we call this value right here a critical value, where this critical value is defined, again, the same thing we talked about previously, where it's the number of standard deviations over to here. So we would call this like Z alpha, because it has alpha to its right. Does that make sense? Derivative of what? What do you mean? Critical value is 0. I mean, critical value is fixed, so derivative would be 0. So then this slope changes based off which critical value you refer to. So anything past the critical value we say is significantly different. We define alpha to be this level of significance. Does that make sense? Right? Sometimes people call it 1 minus alpha, but for confidence interval, it's 1 minus alpha. Does that make sense? All right. Now, a two-sided test would be claiming now that the mean is equal to 50,000, and then the mean is not equal to 50,000. So we would be able to actually get values over here that would be too extreme, and the values there that would be too extreme. But then when you do this, this is alpha, so then we call this one alpha over 2. We call that one alpha over 2. Does that make sense? All right, now I just want to do one example real. You can if you sample enough things. Yep. Well, that's why it becomes impossible to use this process in those types of cases to actually prove something is different, because the problem is there's not that significant of difference. So then you would actually have to get the entire population then. So then so in this case here, if alpha is 0.1 for a two-sided test, that means that alpha, the total sum on these two sides is going to have to be 0.1. Therefore, it's 0.05 here and 0.05 there. Is that correct? So if we want to determine what Z alpha over 2 here is, alpha over 2 would be 0.05. How would you determine what Z of 0.05 would be? What would you type into inv norm? No. What does inv norm expect? What do you have to type in here? You got to give it the area to the left of the position. Is that correct? So 0.95. What is inv norm of 0.95? You should know what the answer is. 1.645. Two standard deviations is approximately it should be 95%. So 2 standard deviations has to be approximately 1.96, right? So then this is approximately 1.645. What's this one then? What did you say? What do I write in here first? What did she say? What are you writing here? How do I find the area for I mean, how do I find the number of standard deviations in this position? 0.05 is correct. If this is 0.05, what does this answer have to be? Negative, because the distribution is symmetric, right? So then this is like the number of standard deviations go this way, the number of standard deviations go that way. Does that make sense? So it's the same really from the previous chapter. Because